All right, so we're going to move on to learning task 2, describe the objectives of bonding from module L1, which is entitled Install Grounding and Bonding Systems. All right, so likewise, most of the code rules that are applicable to bonding are going to be in the same section as grounding in section 10 of the Canadian Electrical Code Book. As far as this module goes, we're going to describe the objectives of bonding. So from learning task 1, you'll remember that grounding can be done to current carrying system components. So current does travel along the neutral, yet the neutral is what we tie to ground. This is versus bonding, which is something only done to non-current carrying parts, like our metal boxes or EMT, anything comprised of metal that is related to electrical. So the metal tabs of our receptacles, they all have to be bonded together, which is going to give them the same equal potential plane. So section 0, which is the definitions part of the Canadian Electrical Code, defines bonding as follows. Bonding is a low impedance or low resistive path obtained by permanently joining all non-current carrying metal parts to ensure electrical continuity and having the capacity to conduct safely any current likely to be imposed on it. So if there is some sort of fault, if a live wire touches an electrical box, you want there to be a path back to the neutral, which is connected to the source. And so that path is then going to be provide enough current to trip the overcurrent protective device. So it's imperative that there's continuity, meaning connection between all metal parts, and that it is also going to be strong enough to conduct safely any current that is going to be applied on it. So it can't just be made of a very thin string of copper conductor or something like that, which could blow apart if there's too much current upon it or melt. Likewise, you want strong connections, because if you have some sort of loose connection, this is why we want to tighten up our lock rings and stuff like that, then you are going to create resistance. And if the more the resistance is, the lower the current, which is, if we make it low enough, then it's not going to trip our breaker, and that's just going to provide another dangerous situation. So it's really important that our connections are strong amongst non-current carrying metallic parts, and that they're going to be sufficient enough to be able to hold any sort of fault current that may occur. So through that definition, we know that bonding must be of low impedance or low resistance. It must be permanent, meaning all the connections are good, that they're not just going to come apart. And this is sort of related. I know we've talked about in the past about EMT. You don't have to run a bond connector through an EMT, because the EMT, being metallic, can act as your pathway of any sort of fault current that may occur. But when we do run a bond through EMT is where it is touching concrete or outside and touching the ground, and that's because the metal can be eaten away, and then we might no longer have that permanency of our path back to ground. It also must be capable of carrying a system fault current. It cannot be a tiny wire that is going to explode if it sees too much current. So our bonding conductors need to be of enough substance to carry any sort of fault current. So the object of this bonding is then defined in Rule 10-2, Subrule 1 of our code books. The object of bonding metal parts and metal systems together and to the grounded system conductor, so back to our neutral, is to reduce the danger of electric shock or property damage by providing a low impedance path for fault current back to the source. Remember that all electrons need to go back to the source, and to establish an equal potential plane such that the possibility of a potential difference between metal parts is minimized. So again, this is when shock, when voltage occurs, if there is any sort of potential difference between one metallic object and another metallic object, and you touch both of those objects, then that potential difference is going to want to even out, and it's going to even out through you if you're connected to both of those, the potential difference. Now, what's critical and what's addressed in our module is the idea of bonding without grounding. Without that bond making its way back to ground, it's going to become a very dangerous situation. So if you take a look at this image here, we got our overhead service going through a meter back to our combination panel. And you'll notice that we have our neutral back here, and we don't have a bond because these are all metallic components. So if we have a fault current here, we got the live wire touching the metallic box. Now all of a sudden that metallic box has electrons flowing through it, and the electrons are flowing back through the conduit back to the panel. Now that whole panel becomes energized as well, and it doesn't have anywhere to flow, doesn't have anywhere to go back to. It wants to go back to the source, but it cannot, and that's because this bond jumper here is detached. So normally, if it were attached, the electrons would be able to flow back through the EMT, back to the combination metallic box, through the bond jumper into the neutral bus, and that neutral bus goes back up to the source. You would see a huge amount of current being drawn through the box and the EMT, and that's going to trip the breaker and everything would be all good. But without that, now everything has become energized, and there's a potential difference between this point and ground. So if someone comes along, indicated by this voltmeter here, and touches even just the box, now they are going to get 120 volt shock. Or if they touch the EMT, 120 volt shock. If they touch any sort of metallic components, they're going to be shocked. So it's really important that the bond is absolutely useless, and actually probably more dangerous if it's not connected back to ground via this bond jumper here. So with the bond connected to ground, now there is a path for stray electrons to flow back to the source. If the bond is made up of solid connections, as it should be, then the resistance should be low and there should be enough current to trip the breaker. Everyone is saved. And so in this situation here, the bond is connected, which provides a path from the fault current through the bond connector to the neutral, back in behind the main breaker, up the neutral conductor, back to the source, which is their transformer. And the breaker trips. And we've identified the fault current before anyone gets shocked or even worse, electrocuted. So another reason that we bond is to eliminate any sort of potential difference. So it gives the example in figure 3 and 4 of our modules about potential differences between metallic components that are run near AC power lines. So as we've discussed in module A3 when it comes to magnetism, we know that when current flows and is changing direction, flux lines are going to be expanding and contracting out of these power lines. And if there are metal objects that are close enough, those flux lines can cut through those metallic objects. And we know that electricity, that voltage, is generated when flux lines cut through metallic objects or conductors. So this would be our conductor here. Flux lines are contracting and expanding across it. Now we all of a sudden have what we call induction has occurred. So we've got voltage induced in this metallic object. So depending on how close it is, remember voltage is related to the distance and the density of those flux lines. The density is related to the distance. So if you'll notice that this metal object is 70 volts, is closer to the power lines, whereas this metallic object, further away from the flux lines, there's gonna be less voltage induced in that. Now there is a difference between this point and this point of 40 volts. So if this fella here is to reach and touch that metallic object and then that metallic object, they would experience a 40 volt shock. If they were to touch simply this object here and then be grounded, then they have the potential to be shocked with 70 volts. So to avoid something like that from happening, and you'll see this wherever you see high transmission power lines and metallic objects, you need to bond everything together, and that's gonna all of a sudden provide a path so that the pressure, which is voltage, is going to be able to be released through this conductor, and everything is going to equal out because these are now essentially the same object. There's continuity between the two. There is no voltage, no pressure relative to this point here and relative to ground. They are all connected, and so this person can walk away, they can walk around, they can touch anything, and they're not going to experience any sort of shocks. So it's really important to do that, especially around power lines. Okay, the other thing that addresses, and this is found on page 28 of module L1, is the importance of bonding non-electrical related metallic components. So there are a few situations where it can be absolutely, it can be very dangerous if components within your house became energized or touched a live wire if they were not bonded to ground. So for example, water piping made of metal. This isn't used so much anymore. Generally, they use PVC. But if you imagine metallic piping in an older house or something like that, or in a commercial building, if a live wire touched it somehow, and it wasn't connected to ground, then all of a sudden that metal water piping would become energized, and that metal piping could be connected to your taps at the sinks or your hot water tank. And if you can imagine going to wash your hands and touching the tap, getting 120 volt shock there, that could be catastrophic. Another one is your septic piping, so all your drain piping and stuff like that. If that became energized, you could imagine going to take a shower and you got a metal pipe coming up. That becomes energized because the live wire has touched it. That can be very shocking indeed. Or again, sink drains, or if you went to go it can be bad. Anytime water and electricity mix, it's usually not a good situation. And the third is gas piping made of metal. So not only could this energize gas-fired appliances, if there's continuity. But it could even cause an explosion if arcing were to occur. So really important that you bond those. So this figure 5 indicates how that would work. And when I worked in residential, generally we didn't worry about water. That was PVC or plastic piping, but we always made sure to bond the gas line, and you do that with a clamp that clamps onto the metallic gas line and then terminates on a bond conductor. Usually number 6 copper is what we would use, and then that goes back into the bond in your panel, which is connected to ground. So I won't go into it, but Rule 10-406 of Rule 2 to 4 lays out that those are the components in your house that need to be bonded to ground. Gas, again, is probably the most important. And if you're dealing with metal water systems, then you only have to worry about it if the entire system is comprised of metal. Whereas gas, any sort of sometimes they'll use like a sort of a flexible non-metallic gas line. You'll see that quite often, but any metallic lines that are connected to that flexible non-metallic line need to be bonded. So you can see in this image here that it's bonded back to ground. There's continuity between this point, and then you got to provide a jumper where this flexible non-metallic gas line is used so that this becomes bonded to ground as well. And the other thing we got to worry about on page 30, it talks about bonding cable coming into your home as well as telephone. So if you what they do is they bond it to ground, and this is usually the structured cabling folks who worry about this. I've never worried about this doing electrical in residential home, in a single dwelling home, but they're gonna bond these two components here to ground. You can imagine that if there were any sort of fault within the system exterior to the house, you don't want that fault entering in through these conductors and then back into your house. One fault could wipe out everyone's cable TV or telephone. So they bond it. This is to prevent faults from exterior network from entering the house, as well as faults from occurring in the interior of the dwelling from affecting the network outside. So if you had a fault somehow inside the house, you don't want that affecting all your neighbors and everyone that uses that same grid. So they bond it to ground right at the box before it enters and exits the house. And that is bonding learning task 2. So hopefully that helps as well, and you're a little more confident about what grounding and bonding is, especially leading in to our standardized ITA exam on January 25th. Right?